Hello everyone, this is Dr. Young, and in this video, we're going to talk about how to assign RNS configurations to chiral centers. So, first of all, just a reminder, chiral centers, what we're talking about here is we're talking about carbons with 4 unique groups. So, carbons with 4 unique groups attached to them. Right, so each of the 4 things on that carbon has to be different. And since there's 4 groups, right, we know that this has to be an sp3 carbon then, right? Because if it only had 3 groups, it'd be sp2, and if it only had 2 groups, it'd be sp. So let's take a look at this first one down here. If I'm looking at like this carbon out here, this is clearly not a chiral carbon because there's 3 H's on it, right? And so those H's are identical, therefore they're not unique. So that carbon that I drew in blue is not a chiral carbon. But if I go over here and I look at this carbon, the second to the left here, this carbon has a CH3 group on it, right? It has a CH3 group. It has this propyl group, the CH2, CH2, CH3 group. It has the chlorine and it has an H, right? Those groups are all different. A methyl group is different than a propyl group, which is different than a hydrogen, which is different than a chlorine. So then, therefore, I know that this carbon right here, that is a chiral carbon. That's a chiral center. And that's the type of carbon that I'm going to need to assign RNS for. If I look at my molecule over there to the right, I see a whole bunch of sp3 carbons, like this one right here, for example, that has an H and an H and an ethyl and whatever this whole big piece is over here to the left. But again, because there's 2 hydrogens, those are not different from each other, so it's not a chiral carbon, right? We have to have 4 different groups. If I take a look at one of these carbons right here in the alkene, definitely not going to be chiral because I don't even have 4 groups, right? I have 1, 2, 3 groups coming off of it. I don't even have 4 groups, so that's not a chiral center. It might be a stereo center, and we can talk more about that later, but it's not a chiral center. It doesn't have central chirality because it doesn't have 4 unique groups on it. So that molecule actually has no chiral centers. Same thing for this alkyne down here, right? If I look at this alkyne, this carbon, that's not chiral because it has a methyl up here and a methyl down there. Those are identical, so that's not chiral. These carbons in the alkyne only have 2 groups attached to them, so they're not chiral. This carbon right here has 2 H's, so it's not chiral. This is a CH3. Those have 3 H's. That's not chiral either. So that molecule has no chirality either. But again, if we look at the molecule over here on the right with the alcohol and the iodo group, this carbon would be considered chiral because we have the OH is different than the H that's attached. And the leg as you move clockwise here is different than the leg if you move counterclockwise there. Yes, there's both a CH2 there and a CH2 there, so that seems the same. But you keep on going out until there's a difference. So if I keep on going clockwise, 2 carbons over, I have an iodine. If I go counterclockwise, 2 carbons over, I don't. So those are different groups. Those are different legs of the ring. There's a difference there. Therefore, that carbon is chiral. And I could do the same thing for where the iodine is attached. This carbon right here is also chiral because, again, at that carbon, you have 4 different groups. And then lastly, with these bottom ones, hopefully by now you're seeing, right, especially if you see a carbon drawn that has a dash or a wedge, you should really look at that closely and make sure, and at least check to see if there's chirality there, because chances are there is. So what we need to do with this RNS configuration business is I need to know, right, both of these down here, these are both 2-bromopropane, right? So this sucker is 2-bromopropane, and so is the other one. Or sorry, not propane, butane. So 2-bromobutane. And I need to tell the difference between these two. I need to know, am I talking about the drawing that I have here on the left, or am I talking about the drawing I here have on the right? And so that's what we use RNS configurations. So how do I figure out what's R and what's S? That's what we need to talk about in this video, right? Because on the left-hand molecule here, this conformer, this isomer right here is R. And the one on the right-hand side, that one's S. And so what I do is I say, oh, this is R2-bromobutane, and the molecule over here on the right, this is S2-bromobutane. And so how do we figure out RNS? How do we determine RNS? We follow what's called the Kohn-Ingold-Prelog rules, the CIP rules, and what we need to do is we need to assign priorities based on atomic masses. And notice that it's an atomic mass. It's not the atomic number. It's not like the molecular weight of the whole group. You just look at the atoms around that central carbon. So from a molecule on the left here, right, here's my chiral carbon. Here's that central carbon. I have 4 unique groups on it. The thing that I'm missing here is an H, right? So I'm going to put my H on here. Remember that when you add your hydrogen or if you add your hydrogen, right, that the dash and the wedge need to be on the same side as each other. It doesn't matter if the H is leaning to the left or to the right of the chlorine. That's irrelevant. Just that it's in back and that you draw it up like that. So then I need to assign my priorities based on atomic mass, right? So I have a hydrogen that I'm comparing versus right here I have a carbon versus here I have a bromine versus here I have a chlorine, right? That's all. It's those atoms that I'm comparing to one another. And so the heaviest one gets the highest priority. So my heaviest atom here is bromine. My second heaviest atom is chlorine. My third heaviest atom is carbon. And my lightest is hydrogen. That's my lowest priority. And I'm just going with the periodic table, right? I'm just literally looking at their atomic masses. Hydrogen's is about 1. Carbon's is a little above 4. Bromine's more closer to 80. So I'm just going by the atomic mass from the periodic table. And then what you do is you're supposed to view it from the point of view where you have the lowest priority group in the back. And so for me, I've already done that. For me, so my lowest priority group is in the back. My hydrogen is my lowest priority group, and it is already in the back, right? It's going away from me. It's in the back. I'll put / away. So I'm already looking at this from the correct point of view. And then what I need to do here is I need to draw a circle from my number 1 to my number 3. So I'm going to go 1, 2, 3. So I drew a circle from my 1 to 2 to 3. And now if that circle goes clockwise, that's the R configuration. And if your circle is going counterclockwise, it's the S. So in mine, I'm going counterclockwise. So this is the S conformation of this molecule. This is the S isomer. So I assign S to that chiral center. And that's basically the gist of those rules, right? And we're going to do some more examples here. And like, what if the lowest priority group is not in the back? What do you do? So let's look at the molecule on the right. You should probably pause, give yourself a second, see if you can figure out what the lowest priority groups are, or what the priorities are. Hopefully you took a crack at that here, right? I need to add my H again. Again, my H is in back, but I haven't put it on the same side, right, as where that wedge was, because always the dash and wedge go next to each other. And again, I'm going to assign my priorities here. So in this case, my highest one is the O. Oxygen weighs more than carbon does. And then I have D. If you haven't seen D in a while, D is deuterium. So D is deuterium, right? Deuterium is just a heavy isotope of hydrogen. It's a hydrogen that weighs 2 instead of 1. But since that weighs 2 and a hydrogen weighs 1, it actually is the third highest priority and hydrogen's my lowest, right? Because again, we go by atomic mass. Deuterium weighs more than hydrogen, therefore it's a higher priority than hydrogen is, right? These are the rules that Kahn, Ingold, and Prelog came up with. So I've got my 1, 2, 3, 4. Again, it looks like my lowest priority group is already in the back, so I'm set as far as that's concerned, and I draw my 1, my 2 to my 3. This time I'm going clockwise, and I have an R configuration. Now you notice that 4 is not in this at all. You just totally ignore the 4. You just go 1, 2, 3. Whether you go clockwise or counterclockwise, you just ignore the 4 completely. So I have one S isomer and one R isomer. These are different molecules, but they have mirror images also. So what do we do when we have ties, right? And all of those atoms were different. I didn't have to come up with any tiebreaker. But if I look at this chiral center here, right, I've got a chlorine. Let me go ahead and put the H in here. Got my H going away from me. So I've got a chlorine versus an H versus a carbon versus a carbon. And that's what I mean by a tie, right? Clearly my chlorine is number 1. My hydrogen's my number 4. But I've got 2 carbons. So what's my 2 and what's my 3? And so the idea here is what you do is when you have that tie, right, you're going to stay at that atom and compare the highest priority group attached to it. So here's the atom I'm at. I'm at this blue carbon here. The highest priority that this carbon is attached to, in this case, is another carbon, right? So for this carbon right here, the highest priority group attached to it is another carbon. For this carbon right here, the only things that it's attached to are hydrogens, right? So for this carbon right here, the only thing it's attached to are hydrogens. And so I have to compare this one's hydrogen to this one's carbon, which means that this group on the right-hand side, this propyl group, has a higher priority than this group on the left, right? Because this carbon beats this hydrogen is the idea. So we're able to break the tie. Now, if there was still a tie at that highest priority, we'd go to the second highest priority. If those tied, we'd go to the third highest priority. If those tied, we'd go out another set of atoms and start that whole process over again. Once you've done that, once you've assigned your priorities, then all the rules are the same, right? So in this case, my lowest priority group is in the back, check. I draw a circle from 1 to 2 to 3. It looks like I'm going clockwise in this case, so that's an R configuration. That's an R. If I take a look at the molecule on the right with this alcohol, same deal. I've got a hydrogen. I'll go ahead and draw my hydrogen in back there, right? The one that's not explicitly drawn. And again, I have hydrogen versus oxygen versus carbon. So I've got a 4 and a 1. That's pretty clear, but I have a carbon-carbon tie. And so now I'm looking at these two carbons and I'm going to ask myself, what's the highest priority thing that they are attached to, right? This carbon on the left has a hydrogen, a carbon, and a carbon. The carbon on the right has a hydrogen, and a carbon. So the carbon on the left's highest group is a carbon. The carbon on the right highest priority group is also a carbon, so that's a tie. So then I have to go, right, so that's its highest priority group on those blue carbons. That's a tie. So what I'm saying here is that now I have to go to the second highest priority. And so for the left-hand carbon, the second highest priority group is a carbon. And on the carbon on the right, the second highest priority group is a hydrogen. And that's enough for me to break the tie, right? This carbon beats this hydrogen. So therefore, this group on the left, sorry, that's a 3. This group on the left should have my second highest priority, and the group on the right should have my third highest priority. And so that's an example of where I had to go to the second highest priorities here, right, for that group. Now, again, had those second highest priorities also been tied, I would have gone to the third highest priorities, is the idea. Once again, my lowest priority group is already in the back, so I just draw 1 to 2 to 3, and it looks like I have yet another R configuration for these molecules. So now what do I do if the lowest priority group is not already in back, right? All of those examples, I had the lowest priority group in the back, so I was able to just draw a circle from 1 to 2 to 3 and figure out if it was R or S. What you can do if you have a case like this here, right? So in this case, my number 1 is the oxygen. I have a 3-way tie with the carbons. If I go through those rules I was just talking to you about, this would be my number 2, this would be my number 3, this would be my number 4. And again, it's not atomic mass, it's just about where do you have ties or not have ties. And so if I look at this now, right now my lowest priority group is in the front. So lowest priority group is in the front. So anytime it's in the front, what you can do is you can just go ahead and take the configuration anyway. So 1, 2, 3. If I go 1 to 2 to 3, it looks like this is R, but I know that I'm looking at it opposite. I know that it's not really R, right? Because the lowest priority group is in front and it's supposed to be in the back. So I know I screw this up. So if I take it anyways and it looks R, I can just switch it and make it S, right? You just switch the configuration from whatever you thought it was, make it the other thing, right? So I thought this looked R. I know I'm wrong, so I just change it to S. It's just a really easy way to get the right configuration without having to do any sort of fancy manipulations. So let me show you that again with another molecule here. So for this one, right, I've got an H coming out at me. That's my lowest priority group. Bromine's number 1. It's definitely the heaviest. The group on the left has a higher priority than the group on the right because what we do is we treat double bonds as like another bond to carbon. You make this little ghost thing, and you can look in books, and we can talk about that later in future videos. But you treat double bonds as being like an additional bond to that thing, right? So it's like saying that this carbon right here has 2 bonds to carbons, this one and this sort of ghosty one, this pretend one. So I got 1, 2, 3. Regardless of that, so I know my lowest priority. It looks like I have an S, but my lowest priority group is in front here, which is the problem. So I'm not going to, I know it's not S, it must be R. And that's the R configuration, right? So 1, 2, 3, it looks S. I know I'm wrong because the lowest priority group is in front, so I can just switch it. So anytime that lowest priority group is just in front, just take the configuration anyways and switch it. Just know that you're exactly wrong. So just switch it. Now, if it's in the plane of the paper, in the plane of the board, in the plane of your screen, the idea is you have to do a little bit more manipulations to kind of get it to be easy. Again, you can visualize this sort of like three-dimensionally. You can build models. You can do things like turn things into Fisher projections and manipulate those. But another way you can do this is just by switching the lowest priority group with whatever's in the back, taking the configuration, and then switching it. So let me show you what I mean here, right? So if I look at this one, my number 1 is chlorine, my number 2 is the ethyl, my number 3 is the methyl, my number 4 is hydrogen. And this is what I mean by it's in the plane of the paper, right? The hydrogen isn't a dash or a wedge, it's a straight line, which means it's in the plane of the paper, in the plane of your screen here. So it's in the plane, so it's not coming out at me, it's not going back. So I can't just take it and be right. I can't take it and switch it. I have to do a little bit of manipulation. So what I'm going to do here is I'm going to, like I said in the instructions up here, I'm going to take whatever my lowest priority group is, so my number 4 here, and I'm going to switch it with whatever's in the back, which is my number 1. In this case, it's my number 1, right? Because the chlorine's in the back. It's the dash. So now I'm going to call this 4. I'm going to call this 1. But what I've done is I've messed up the molecule. I changed the molecule. And so whatever configuration I'm about to figure out is wrong. And so if I take this configuration, I know I'm not actually taking the configuration of the original molecule. I'm taking the configuration of this new switched up, messed up molecule that I did. So now I can go 1, 2, 3. It looks like that's R, but again, I did this switcheroo here. So I did the switcheroo, so I really need to change it to S. And that will get you the right configuration. I know it feels kind of weird and feels kind of funny, but it works. Ditto, if I go to this molecule on the right-hand side, let's see, my number 1 is over here is this propyl piece. My number 2 is the methyl. My number 3 is the deuterium. My number 4 is the hydrogen. Again, the hydrogen is not coming out or going back. It's in the plane. So again, I'm going to switch it with whatever is in the back. So I'm going to switch number 4 with, in this case, number 3, right? Because number 3 is in the back. So I'm going to change this to 4, change this to 3, and I'm going to go ahead, I'm going to take my configuration and switch it. So now I'm going 1, whoops, let me go back here. So now I have 1, 2, 3, right, which looks like R, but again, I know that I'm wrong, so I need to switch it to S. So I'm going to switch it to S. So here I have an S configuration of this molecule. And you'll be right every single time. If you try to just take the configuration, you have a 50-50 chance of being right or wrong because you're not looking at it right. If you try to take it and switch it, you have a 50-50 chance of being right or wrong because you're not looking at the right molecule. This is the only way that you can get it right 100% of the time. If you do this, you'll get it right 100% of the time, assuming that you've assigned your priorities right and everything. And then lastly, like I said, or if you're really good at just visually picking up the molecule in your brain and turning it so that that lowest priority group is looking away from you, that works great. Also building a model kit and looking at it the right way so the lowest priority group is going away from you, that works great too. So these are just strategies for you to have in front of you, to have in your pocket here, so that when you see something on paper, you can just do these operations to get the correct RNS configuration. So I hope that helps. You definitely should practice 100,000 of these. The more you practice, the faster you get. And you only have 3 situations. Either the lowest priority group is going to be in back, it's coming out at you, or it's in the plane. And then you can figure out your RNS configurations. So practice up. Happy studying.